Today we're going to talk about the best or top 10 op amps in the market today. But first we're going to talk about how to select the proper op amp. Now, a lot of people have told me that the 741 is obsolete, and up to a certain extent, I do agree. It's old, but old sometimes is good because they're reliable and we know it works. And if it works, sometimes it's better to stick to it. But that's beside the point. We're going to talk about what makes, according to experts, the op amp the best. So, what makes an op amp the perfect amp? Let's start with the ideal gain. According to SourceEngine.com, an ideal op amp will have infinite open loop gain, infinite input impedance, zero output impedance, and an infinite frequency response with zero noise and no distortion. Realistically, no op amp can satisfy all of these requirements. General purpose op amps will work well in many circuits. However, some applications may require higher performance from a specialty device. To meet the varying design requirements of different applications, engineers should consider several factors to ensure they select the proper op amp. These key attributes are detailed below. First is gain. One of the most distinctive characteristics of an op amp is high gain. Gain measures an op amp amplification factor, or how much larger the magnitude of its output is compared to its input. It's typically called an open loop gain, or a larger signal voltage gain. An open loop gain measures a device gain without positive or negative feedback. When listed, the open loop gain represents the maximum AC gain at very low frequencies. Ideally, an op amp gain should be infinite, but real values usually range from 20,000 to 200,000 ohms. By comparison, a larger signal voltage gain, aka AVT, depicts the ratio of the output change to the input's differential voltage shift. It is measured at low frequency DC, and the amplifier produces a larger voltage output. It is typically preferential to an open loop gain, usually as V over millivolts. Notably, this gain is measured without an op amp. Without an output load, which accounts for loading effects. Next is the number of channels. The most common number of channels for an op amp is 1, 2, or 4. However, they can have as many as 8 channels. Input and output impedance. An op amp input and output impedance generally shows the relationship between voltage and current. Input impedance shows how much more current will flow as the voltage increases, or how much less current flows when the voltage is decreased. Actual op amps have a very high input impedance. Typical values can be hundreds of millions of ohms. A prime advantage of high input impedance is that minimal current is needed from the source to the produced voltage. Ideally, this value should be infinite. Output impedance, on the other hand, is ideally zero. However, most AC-based op-amps have output impedance values of less than 1/100th of an ohm. Bandwidth and gain bandwidth product. An optimal op-amp will have an infinite bandwidth and be able to amplify any frequency signal from DC to the highest AC frequencies. However, bandwidth for actual op-amps can only amplify sound through a specific range of frequencies. Once it exceeds its frequency limit, the device can produce sound. The gain bandwidth product, or GBP, describes the frequency at which the op-amp's amplifier becomes unity gain. The factor allows designers to achieve the maximum gain an op-amp can produce for a given frequency. Slew rate. An op-amp's slew rate is the change in the output voltage caused by a step change of the input. It is measured as the ability of a device to change its output voltage by a certain amount of a given amount of time. An op-amp should have an infinite slew rate in a perfect world, meaning the output from the amplifier will be a distortion-free amplifier copy of the input. Engineers should also be aware that the slew rate change values vary according to the type of op-amp used. In actuality, the higher the slew rate, the faster the output can change. So, low-power op-amps might yield a slew rate value of 1 volt per microsecond, while faster op-amps can produce rates as high as 1000 volts per microsecond. Noise. The perfect operational amplifier will have zero noise. Unfortunately, all op-amps contain several internal noise sources, such as a current, resistor, more. They are measured at the output and referred back to the inputs. The equivalent input noise voltage is the most significant noise type, and it's also bandwidth dependent. Overall, designers should aim for this noise value to be as small as possible. Maximum input offset voltage. Due to the manufacturing imperfections, differential input transistors in actual op-amps may not match precisely. In both op-amp input were zero, it would produce zero output. Thus, a small differential input voltage must be applied to force a zero output. It is called input offset voltage and should be a small value. Maximal supplied voltage. Overall, engineers should consider these factors and how they impact each application-specific design requirements when deciding which op-amp to use and for a project. What type of project? First on the list is OPA 310 SIDCKR, Texas Instruments Incorporated. This single high-output current operational amplifier offers a minimum supply voltage of 1.5 to 5.5 max. The entire OPA family features a fast shutdown response and typical enabled time of 0.9 microseconds, which allows for power savings when the application involves recycling the amplifier signal chain. The OPA 310S in particular are single amplifiers with rail-to-rail input and output swing capabilities. To provide robust ESD performance, the OPA 310 is a fail-safe input ESD structure with no diodes connected from inputs to the positive power rail supply. The simplified design features an integrated RFI and EMI rejection filter with a known phase reversal in input overdrive conditions. As such, the op-amp also delivers superb AC performance with a gain bandwidth of 3 MHz. Designers can achieve improved performance and lower power consumption when utilizing the OPA 310. Second on the list is the ST Microelectronics TSB712 IYSD. These 6 MHz bandwidth amplifiers are precision amps with rail-to-rail input and output guaranteed to operate from plus 2.7 volts to plus 36 volts single supply, and from plus or minus 1.35 volts to plus or minus 18 volts. Dual supplies for these components in the TSB7 family. These amplifiers offer a large supply voltage span and an excellent input offset voltage of 300 microvolts maximum at 25 degrees Celsius, specifically plus 36 volts for the TSB712 IYSD. The TSB712 IYSD can be used in various industrial applications such as filters, power supplies, and motor controls, actuator driving, Hall effect sensors, and resistive transducers. Third on the list is the Microchip Technology Inc. MCP 6499-E SL. This single supply op-amp can supply voltage as low as 1.9 volts while only drawing 2 milliamps. Amplifier typical of quiescent current. The MCP 646-6R-6U-7-9 series all possess a low input bias current and rail-to-rail input and output operation. This op-amp has a gain stability of 300 MHz with an input bias current of 1 picoamp. The MCP 6499 is recommended for automotive applications. Each op-amp within the MCP 649 family is integrated with EMI filtering to mitigate the high-frequency electromagnetic noise. All op-amps including MCP6499-E-SL are fully specified over the extended temperature range from minus 40 degrees Celsius to plus 125 degrees Celsius. Fourth on the list is the Texas Instruments Incorporated OPA 2391 YBJR. The dual micro-power precision op-amp with the DSPGA package, the OPA 2391 YBJR features a unique combination of high bandwidth 1 MHz and very low quiescent current 24 microamps. It combines rail-to-rail input and output with an ultra-low input bias current of 10 femtoamps. 1 femtoamp is basically 1 trillionth of 1 amp. So, if you look at the chart, you can find it in Google or anywhere else. It's basically minus 15 positions after the dot. So that will be a trillion. 1 femtoamp is basically 1 trillionth of an amp. And only 45 microvolts of offset maximum and 1.2 microvolts Celsius of drift over temperature. This helps the op-amp maintain high precision and ratiometric and amperometric sensor front ends, which often have demanded low power requirements. It is an exceptional op-amp in high gain and lower applications. Specifically, the OPA 2391 utilizes proprietary eTrim operational amplifier technology, enabling a unique combination of ultra-low offset and low input offset drift without input switching or auto zero techniques. This Texas Instruments technology tolerates high output capacitance to alleviate stability problems that are exceedingly common in low power amplifiers. Next on the list, number 5 is ST Microelectronics and B. TSZ181HYLT. This op-amp is a single operational amplifier with a very low offset voltage with virtually zero drift versus temperature changes. The TSZ18H operate over an extended range of minus 40 degrees Celsius to plus 150 degrees Celsius and features an ultra-low input bias current with an excellent speed and power consumption ratio. An AEC-Q100 is a failure mechanism-based stress test qualification for a packaged integrated circuit used in the automotive applications. This specification has been established by the Automotive Electronics Council, or AEC, to define qualification requirements and procedures for packaged integrated circuits used in the automotive industry. Basically, an AEC-Q100 qualified device means that the device has passed the specified stress tests and guarantees a certain level of quality and reliability. Number 6 on the list is Texas Instruments Incorporated LM290-2BIPWR. This quad op amp offers 4 independent high-gain frequency compensated op amps designed to operate specifically from a single supply over a wide range of voltages. Operating from split supply is possible when the difference between the two supplies is 3 volts to 36 volts. For B version devices, 3 volts to 32 volts for version. For V version devices, or 3 volts to 26 volts for all other devices. And BCC is at least 1.5 volts more positive than the input common mode voltage. As a result, all of the low supply current drain being independent of the supply voltage, the applications for the LM290-2B-Q1 include transducers, amplifiers, DC amplification blocks, and conventional operational amplifier circuits, which can be easily implemented with a single supply voltage system. Number 7 on the list is onsemi NCV33204DR2G. This quad op amp provides input capabilities that can be driven as high as 200 volts beyond the supply rails without output phase reversal. Outputs can swing within 50 millivolts of each rail, with rail-to-rail operations that fully uses the supply voltage range. It is designed to work at a very low supply voltage, plus or minus 0.9 volts, yet can operate with a supply voltage of up to plus 12 volts and ground. The NCV33204DR2G can output current boosts to its high current output current capability without raising the drain current beyond a minimum. A combination of low noise and distortion with a high slew rate and drive capability makes this an ideal amplifier for audio applications. Next on the list is Texas Instruments TLV9361 IDBGR. This op amp offers strong DC and AC specifications with rail-to-rail output and EMIRR filtering for automotive needs. It has a low input voltage noise density, low offset, and low offset drift at a 10.6 MHz bandwidth. This single op amp is an AEC-Q100 automotive qualified and cost optimized. The TLV9361 IDBVR also features high output current of plus or minus 60 milliamps. and a high slew rate of 25 volts per microsecond. It has an HBM ESD classification level of 2A and a CDM ESD classification level of C6 under AEC-Q100. Keep in mind that the EMI-RR means rejection ratio of operational amplifiers. HBM ESD, CDM ESD classifications, they basically mean that their semiconductor devices include protection circuitry, but to ensure their effectiveness and reliability requirements as per the JEDEC standards, ESD tests are required to qualify parts. There are three different main test models for the ESD test: the human body model, HBM, the charged device model, CDM, and the machine model, MM. So those are just basically standards of testing the devices. Now on the list is ST Microelectronics NV. This dual op amp with a 50 MHz bandwidth unity gain stable amplifier. It has excellent accuracy provided by a maximum input voltage of 200 microvolts, allowing amplifying accurately small amplitude input signal. The op amp can operate from 2.2 volts to 5.5 volts single supply with a capability to handle an output capacitor of up to 1 nanofarad and is fully specified on a load of 22 picofarad, therefore allowing easy usage as AD converter's input buffer. The rail-to-rail input stage and the slew rate of 30 volts per microseconds makes it ideal for low side current measurement. The benefits of the TSV92I-YST are that the measurement accuracy is virtually unaffected by noise or input bias current, and its signal conditioning is excellent for high frequencies. TSV92I-YST are that the measurement accuracy is virtually unaffected by noise or input bias current, and its signal conditioning is excellent for high frequencies. Next on the list is Texas Instruments Incorporated OPA 817DTKR. This is an 800 MHz high precision unity gain stable FET input operational amplifier for various dynamic applications. Equipped with a low noise junction field effect transition or JFET input stage, the OPA 817 features a wide gain bandwidth of 400 MHz and a supply range from 6 volts to 12.6 volts. The fast slew rate of 100 volts per microsecond allows a wide, large signal bandwidth and low distortion when used as a high impedance buffer in high-speed digitizers, active probes, and other test and measuring applications. This op amp offers a combination of picoamps of input bias current and low input voltage noise, which makes the OPA 817 ideal for instrumentation in applications with strict requirements. such as medical and scientific testing. It is also available in an 8-lead WSON package with an exposed thermal pad for heat dissipation. So that's it for today, guys. Thank you so much for watching. In the description of the video, I'm going to put the links to all the documentation and specs for all the amps we talked about today. Thank you again, and please like, share, and subscribe. Thank you and have a good night, and we'll see you all tomorrow.